Welcome to the IMechE webinars. We are really pleased that you can join us for this very exciting talk on smart remanufacturing. I'm Konstantinos Salonitis. I'm the chair of the Manufacturing Industries Division. And of course, in my everyday job, I'm a professor of manufacturing systems and the head of Sustainable Manufacturing Systems Center at Cranfield University. I am really pleased to welcome Professor Doug Pham. Doug holds the Chance Chair of Engineering at the University of Birmingham, where he started his career as a lecturer in robotics and control engineering. So before returning to Birmingham in 2011, he was professor of computer-controlled manufacture and the director of the Manufacturing Engineering Center at Cardiff University. He has an impressive research track record in the areas of intelligent systems, robotics, autonomous systems, advanced manufacturing, and remanufacturing technology, which is the topic of the talk today. He has published more than 600 technical papers. He's got many books authored. He has graduated more than 100 PhD students, a really impressive track record. He's the recipient of several awards, including 5 prizes from the IMechE, the Institution of Mechanical Engineers, a Lifetime Achievement Award from the World Automation Congress, and also a Distinguished International Academic Contribution Award from the IEEE. The talk today is on robotic disassembly as an enabler for smart remanufacturing. Remanufacturing is a vital component of the circular economy, allowing us to save resources and drastically cut greenhouse gas emissions. In a very simple way, it has to do with returning a product that has reached the end of its service life to at least its original condition, with a warranty equal to or even longer than for the original product. So Doug will be presenting today the research into robotic disassembly by Autonomous Remanufacturing Laboratory at Birmingham University. Before handing over to Doug, I would like to remind you all that throughout the session, you can post questions in the Ask Questions tab, and we will be looking into these questions throughout the session. And at the end of the presentation, we will try to cover most of these. Over to you, Doug.
Thank you very much, Kostas, for the introduction. I would like also to thank the Manufacturing Industries Division for supporting this webinar, thus enabling me to present our work. I also would like to thank Molly for teaching me how to use WorkCast. If anything goes wrong, you can blame Molly. I'd like to acknowledge the support of our academic and industrial partners listed here. They include our great friends at Wuhan University of Technology, President Zhou, President of the University of Wuhan University of Technology, Professor Liu and Professor Xu, and the University of Castilla-La Mancha in Spain, Professor Ramirez. The presentation will be divided into 3 parts. First, I will introduce remanufacturing, which may not be well known to some in the audience. The core of the presentation will be about our work on Robotic Disassembly, our Auto Reman research program, which was sponsored by the Engineering and Physical Sciences Research Council. Here is how the British Standards Institution defines remanufacturing. It is the process of returning a product to at least its original performance with a warranty that is equivalent to or better than that of the newly manufactured product. So I've underlined equivalent to or better than. Here's another definition. It is a little bit longer, so I'm not expecting you to read it. I have only highlighted 2 words here, like new or better than new. So your remanufactured product should be like the new product or better than the new product. So that's important to distinguish remanufacturing from other processes like reconditioning and refurbishing. We are all familiar with manufacturing, which is the process of converting raw materials into the product that we use and then we dispose of. Remanufacturing is part of a circular economy. It is this inside loop here that goes from the end of use product, end of life product, to the beginning of the manufacturing process, and then becomes the new product for you to use again. Remanufacturing is the loop that is between recycling and reuse. It is more efficient than recycling. It saves more of the original value of the product than recycling can. It saves the energy that is put into the converting of the raw materials into the product that you use. So it saves the value, it retains more value of the product. Remanufacturing has many benefits. The first type of benefits are to do with sustainability. So you see here, in the remanufacture of a turbocharger, you can save up to 98% of the material. You can save, you can reduce carbon dioxide emissions by 37% in the case of turbochargers. In the case of the starter motor, you save 88% of the raw materials, and you emit 52% less carbon dioxide. Here is another example from our industrial partner Caterpillar, to whom we are greatly indebted. It is no exaggeration to say that without Caterpillar, in particular our friend Scott Mitchell, who is the engineering manager at Caterpillar in Shrewsbury, there would be no auto reman project. In the case of their cylinder head, Caterpillar found that they achieved massive environmental benefits, including a 99% reduction in landfill space required. So this is extremely helpful for the environment. In sustainability research, we often talk about the triple bottom line. Of the three bottom lines, the economic bottom line is, for many, probably the most important. And you can find that with remanufacturing, you can achieve a lot of profits. The manufacturer achieves more than twice the profit of compared to the original manufactured product. The remanufacturer could achieve 2.75 times the profit if the product is leased rather than sold. If the product is sold, then at least 50% more profit. This is despite a large increase in labor content. And this is achieved also because of the savings that I mentioned before. Savings in raw materials, savings in energy. It's not all a bed of roses. There are problems, there are challenges in remanufacturing, and the key challenge is uncertainties. In remanufacturing, there are uncertainties with the supply side. So there is uncertainty in the quality of the product that you receive, in the quantity, in the number of products that arrive, and also in the timing of when they arrive. So these uncertainties cause operational uncertainties, such as variability in the processing routes and times. We don't know how much time a product needs to be remanufactured, because it might take less time if the quality of the product is good. If the quality is poor, the product is deformed, is damaged, then the remanufacturing of the product would take a lot more time. So there are all those uncertainties. Also, there are uncertainties with the demand of the product. Now, those uncertainties are solved by market research. On the engineering side, we can deal with the supply uncertainties, supply side uncertainties, and therefore we can also deal with the operational uncertainties. And how do we do that? We do that by using sensors to sense the condition of the product while it is used, to communicate that condition back to the factory, to monitor the condition of the product continuously. And then with that, we can decide when the product will be ready for remanufacturing. And when it is ready for remanufacturing, we will know the condition of it. And therefore, we can eliminate or at least reduce many of the operational uncertainties that I mentioned before. I need to go back to the previous slide because it jumped too fast. So this shows a smart remanufacturing environment. The work was done in collaboration with our partners in the University of Campania in Italy. And here we look at cloud remanufacturing. We look at the communication between the different factories, remanufacturing factories, using technologies like the Internet of Things and cloud computing. And we use digital twins to model the product, to model the processes, and to model the factory. So this is a concept of cloud remanufacturing that was proposed in this article. Oh, jumped again very fast. Let me just go back to the previous slide. Yes. So here we have a framework for smart remanufacturing. The slide is very busy. I don't expect you to see everything in this slide. You just look at the gray boxes. They represent stages in the smart remanufacturing environment. And the yellow boxes, they represent the enablers of smart remanufacturing. And we see that there are opportunities to work on the product and to look at the product life cycle from the beginning of life to the middle of life and to the end of life. We can study the product and we can make it smarter for remanufacturing. We can look at the remanufacturing system, and there we can have communication between the product and the machines, and between the machines and the whole manufacturing system. So again, there is an article that we wrote and that you are welcome to read, and you'll find out more about what we mean by this smart remanufacturing framework. So let's look into remanufacturing, what it consists of. At the beginning of the process, we have the product, which has to be disassembled. And then the product is cleaned and the components are inspected. Those that need to be repaired are repaired. Those that cannot be repaired, they will be replaced by new components. And then all the components are put together again, and the product is tested. The product that successfully passes the test becomes your remanufactured product. Now, at this point, where do you do repair and replace? You might replace an old component with a new generation component. The new generation component might be stronger, lighter, and maybe even cheaper than the old component. Therefore, the remanufactured product has a chance of being even better than the original product, because now it has some new components that are lighter, stronger, more hard wearing, and so on. These videos show one important point, and the main important point is that disassembly is a labor-intensive process. It's very labor-intensive. The second video on the left-hand side shows that disassembly requires skills, dexterity. The same is shown on the right-hand side video. Dexterity is involved. The right-hand side video also shows a very common disassembly operation, and that is unscrewing. Removal of screws is a very common disassembly operation. Because disassembly is a labor-intensive process, it consumes a lot of cost. And disassembly is difficult to automate because it requires the skills that I mentioned before. So this means that we have a need to conduct disassembly research. We are not the first people to do that. There are many people before us, starting in the 1990s, who looked at robotic disassembly. But what they did was they looked at disassembly problems one by one. They looked at, let's say, the disassembly of televisions, the disassembly of an engine, for instance. So each time they construct a system to do the disassembly, they do it in an ad hoc manner. And if they have a new product, they will have to start again from the beginning. What we propose to do in our project is to look at disassembly from a fundamental point of view. We try to get a fundamental understanding of disassembly processes so that we can create robust autonomous disassembly systems. We apply a systems method to study robotic disassembly, and I will explain that on the next slide. So our project, AutoReman, stands for Autonomous Remanufacturing, consists of 5 different work packages. The first work package is to look into disassembly science. We break disassembly down into different operations and we study them. For instance, here is the disassembly of a pin, the removal of a pin from a hole. We look at how that is done. We look at the informatics and the mechanics involved in the process, and we try to understand the process. With that understanding, we can design strategies to enable robots to perform that operation reliably. And then when we encounter the operation in different disassembly tasks, we can perform the operation easily. Disassembly planning is also important to our project because we want robots to be able to plan their disassembly operations. In particular, they need to be able to replan the disassembly operations because, as I mentioned before, disassembly and remanufacturing are full of uncertainties. So when you have a plan at the beginning, there is no guarantee that the plan can be executed perfectly because during disassembly, there could be some problems and the robot has to be able to replan its operation. Although it will be possible to automate disassembly processes completely, there will be some operations that are not economically feasible to automate fully. And in such cases, it will be useful for people and robots to work together. So we look into collaborative disassembly using humans and robots together. And then the 5th work package is to do with demonstrations. So we implement the strategies into the disassembly of different products. We have so far studied 3 different products. I mentioned all those 3 shortly. Before we started the research, we looked into the disassembly of many products. In fact, we looked into the disassembly of over 400 products. We broke that down into 12,000 operations. And we found that unscrewing is performed in 40% of the operations. Pulling, the pulling of a pin from a hole, as I mentioned before, as you saw before, is another set of operations that is very common. And then separation is the whole lot of other operations. It consists of a miscellaneous group of operations. We so far have focused only on unscrewing and pulling. So 60% of the operations, 40% more are still to be investigated. So we all know that when there are vibrations, screws can become undone. Now, research in the past by engineers in the aerospace industry, automotive industry, marine industry has been focused at preventing the automatic undoing of screws when they vibrate. In our case, we try to promote self-loosening of screws. We have constructed a rig, experimental rig, to study how vibrations can be used to remove screws, to let screws undo themselves. We've done simulation work on the removal of 4 screws simultaneously, and we have built a rig to study it. So here you see the 4 screws, they are undone almost simultaneously, and you can see the loosening of the tension in the screws. That follows the simulation work reasonably well. So the tension in the 4 screws reduces to 0 almost simultaneously. We have built a device which is mounted at the end of a robot arm, and that device can be used to shake products and make the screws loosen. For instance, here, if you focus carefully, you will see the screw loosen. Yeah, the nut rotates. We can use the same tool to unwedge a shaft that is stuck when you pull it out. So you can use the same tool to do the unwedging. Here we talk about how to move the pin out without the pin being wedged. So the clearance between the pin and the hole is grossly exaggerated. In practice, the clearance will be small and wedging is possible. However, if you use a particular strategy known as active compliance, and active compliance involves sensing the force and the moment that acts on the pin as you pull the pin out, and moving the robot in such a way as to reduce the force and the moment, you can prevent wedging from happening. So this is the theoretical study, and this is the implementation of the outcome of the study. The clearance between the pin and the hole is of the order of a few microns. Now here is another strategy for pulling the pin out of the hole without the pin being wedged in the hole. And this uses a device known as the Stewart platform. The Stewart platform, by the way, was a mechanism that was published in the Institution of Mechanical Engineers some 50 years ago, 60 years ago almost. And the device is a 6 degrees of freedom device. It can move in 3 directions and also rotate along 3 axes. So here you see the different movements simulated, and here's the device. And when you put the pin at the end of the device, you can pull the pin out and it won't wedge because it will adapt itself to the shape of the hole. Here is a more recent design of the compliance device, and this compliance device is designed to resist the pulling forces, because when you do disassembly, rather than pushing, often you do the pulling operation, and in pulling the pin out of the hole, you can damage the device, and here the device is designed so that it can resist the pulling forces. Here's another pulling operation. We pull and wriggle the part at the same time. So on the left-hand side, it's a straight pulling. On the right-hand side is the pulling and wriggling. And we have shown in theory and in simulation and in experimentation that by pulling and wriggling, you can reduce the amount of pulling force required. Here's another pulling strategy. You pull and twist at the same time. And again, using simple mechanical analysis, you can show that the pulling force is reduced when you do twisting at the same time. So here we show the pulling force on the right-hand side, the pulling force which is with and without twisting. When you have twisting, which is a red curve, you see that the pulling force is reduced. Here's another type of pulling operation. So the robot on the left-hand side started first. It pulls the pin along the slot. The robot on the right-hand side starts later, but it finishes before. And this is because the robot on the right-hand side uses vibrations. So you can see again vibrations helping disassembly. Whereas in normal operation, we don't like vibrations. For disassembly, we love vibrations. You can see the robot on the right-hand side finishes much earlier than the robot on the left-hand side. In the operation that I showed you just now, the robots were taught how to move. But you can let the robot learn by themselves. So here we use what is known as reinforcement learning. And the robot moves in such a way as to maximize a reward function. So R, big R, is the reward function. It is made up of little r's. And a little r is a function of the displacement of the robot and also the force and moment that it feels. So you can see that little r is large when the displacement is large. So if the robot moves in such a way that the displacement is large, then the reward will be high. Also, if it moves so that the forces and moments are small, then also the reward will be large. So the robot learns by itself to move in such a direction as to maximize R in such a way that big R will be maximized. So here you can see learning. The robot initially fails because it has not been able to learn long enough. So it fails again here after a few episodes. But then towards the end, it will reach the end of the slot by itself. It has not been told to move in any direction. It finds the direction by itself. So learning is a strategy that can be employed. I mentioned planning. So here's an example of a very simple sequence planning problem. We have a pump, a water pump, with 6 components. Here's the first plan. Here's the second plan. Same number of steps are involved. Here's the third plan, a shorter plan. So by optimizing the plan of the disassembly, you can shorten the disassembly time. This shows that optimization can be used in order to reduce disassembly time. This is a simple problem. You have only reduced the disassembly time by 1 step. If you have many parts, then disassembly planning becomes important. You will need to use tools and techniques to optimize your disassembly plan. In disassembly planning, we work with many partners. We work with the University of Technology in Wuhan. We work also with Beihang University in China. And we work with Beijing University of Civil Engineering and Architecture and many other universities. Here we show an example of collaboration with our colleagues at the University of Castilla-La Mancha. And here we have a disassembly of a gearbox. And this, what we want to highlight is the use of a nature-inspired algorithm known as the BEES algorithm to optimize the disassembly sequence for this gearbox. And the aim is to minimize the energy required and maximize profit, as well as maximize the reduction in carbon dioxide emissions, so maximize the environmental benefits. We don't have time to discuss the BEES algorithm or disassembly sequence planning. You can find out more in these books, which have a reason from our work. The fourth area of our project is human-robot collaboration. As I mentioned, there are tasks which, although they are possible to be done by robots, are not economically feasible, because you would need a lot of tools, special tools and jigs and fixtures that would make the cost too high. So you use people for such tasks, and you use robots where the work is repetitive, boring, or even dangerous. We have demonstrated human-robot collaboration in 2 of our case studies. The first case study involves using a human and 2 robots to disassemble that water pump that I showed earlier. And the top video shows the robot handling the pump, moving it to a press. And because this is just a simple demonstration, we use a human to operate the press. And the robot waits for the part to be ready. It waits at the press, and when the part touches its hand, it knows that the part is ready, and then it opens the hand and grasps it. So that's the top video, yeah. And it grasps the part. In the bottom video, the robot holds the part as it is being pushed out. And again, it prevents the part from dropping and maybe become damaged. So in both cases, we show the robot acting as the third hand of the person. This is one way of robot helping people. The robot acting as an assistant, acting as the third hand of the person. Here's the second case study, where we look at the disassembly of a turbocharger. And the work was done in collaboration with our colleague, Reco Turbo. And here we have again 2 robots and a human operator. The top video shows the robot searching for the position of the screw. And because this is a remanufactured product or an end-of-life product, the position of the screw is not completely known. It's not exactly known. So the robot has to search for the position of the screw. It does that by using sensors in its hand, and it goes around in a spiral search fashion, and it finds a screw, and then it unscrews. The bottom videos show the person performing operations that are too difficult for the robot. For instance, requiring a high force or high torque, or requiring tapping and operations that are difficult for the robot to perform. Operations where the robot cannot access because of restricted space. So we have the person doing the job. The third demonstration involves no people. In this operation, we look at the disassembly of a an electric vehicle battery. And because this is a dangerous operation, we don't use people in the operation. We use 4 robots instead. This shows the disassembly sequence involved. First, the top cover is removed, then an electric cable is disconnected, and then we remove the bus bar, and then we remove the battery modules. The numbers here are the numbers of screws that have to be removed. So 35 screws for the top, 1 screw for the electric cable, 4 screws for the bus bar, and this number of screws for the modules. So you can see a lot of screws are required to be removed. We use digital twin technology to model the disassembly operation, the handling operation. And here we use digital twin to model the process of removing screws. So the robot is removing the screws, and the twin is following the operation of the robot. And just to show that the twin is a real twin, you will see that in a few minutes. You will see that the twin is a real twin. It's not a simulation. It actually follows the operation of the machine. Yeah, there we are. IMechE, he moves the robot, and the twin follows the robot. Here's another couple of clips from the battery disassembly operation. The robot has to remove a cable, and it uses its finger to prise the cable off. Now the position of the cable is not known because the cable has just popped off. The robot has to look for the cable. So it uses a 3D camera, it looks for the cable, finds the cable, it moves, it pulls the cable off. The ties are broken. And at this end, the cable is stuck. And the robot has to find the cable again. And it comes and picks up the cable, and it wriggles it, just like we would do. And then it removes it. It uses vision sensor to find the cable. It uses force sensor to detect when it has managed to pull the cable out. So, in conclusion, we know that remanufacturing is good for the economy and the planet. We know that disassembly, which is the first operation in remanufacturing, is very labor intensive. Our project, AutoReman, has taken an initial step towards understanding disassembly. And this will help us design strategies to enable robots to perform disassembly operations in a robust manner, so that when we go to different products, we can use the same strategies. We don't have to go back to the beginning and design everything from the beginning. So we believe that dawn has broken, and we will see the beginning of smart, autonomous remanufacturing in the future. But does this mean that it's the end of disassembly research? Certainly not. Now, this slide shows a Science Direct topic known as the pack-in-hole topic. Pack-in-hole is the topic of research by many researchers, beginning in the 1960s with the paper by Savitchenko and Bespalov in the Russian Engineering Journal. And that paper sparked off a lot of studies into how to put a pin into a hole, how to insert a pin into a hole. So in 1967, there was another paper from the Russians. And then in 2022, there are still papers. And if you look at 2023, you will also find some papers on how to put a pin into a hole. Our first paper on how to pull the pin out of the hole was published in 2019. I believe that in 20, 30, 40 years' time, there'll be more people studying that process and the many processes that we have uncovered that we are still not studying. So it's not the end of robotic disassembly research. And as the EU Commissioner for the Environment said, in remanufacturing, there is a big opportunity, and there is a lot of research to be done, as you can see. We cannot do it on our own. We welcome participation of colleagues all around the world. As you can see, we already are working with colleagues in China, in Italy, in Spain. We do welcome partners from other places. I will be talking with colleagues in Singapore soon about collaboration with them. And you are welcome to join us. Every year, we have an event where we discuss our research. And this year, the event will be held in Italy by our colleagues in Italy, and our colleague Marcello Ferra and Mario Catorino will welcome you to attend the event in Italy. Thank you very much.
Thank you very much, Doug, for this excellent and insightful presentation. I'm pretty sure that our audience have enjoyed the slides and enjoyed your talking about remanufacturing. There are a couple of interesting questions, more than a couple actually. There are a number of interesting questions in the QA tab. So let me start by asking you a very simple one. You've presented a number of interesting cases where remanufacturing has been used. Are there any other products or families of products where you can see that remanufacturing could be used more extensively in order to extend the life cycle of products?
Yes, certainly. There are many, many different products in the automotive industry, in the aerospace industry, in marine industry, in the train industry. Many, many different products can be remanufactured. It is very likely that the ink that you use in your printer has been remanufactured. The ink cartridges, they have been remanufactured. So many products, household products, consumer products, telephones, mobile phones, washing machines, they can all be remanufactured, and they are remanufactured. Computers are remanufactured. Mari, who was in our team, she used a remanufactured computer when she started with us.
That's great. A follow-up question to this one. You have presented to us how beneficial remanufacturing is and what are basically the potential benefits and the impact that it can have in saving energy, in saving resources. What are the main challenges or the main barriers nowadays? And as a result of this, remanufacturing is not more widely practiced?
I think the main issue is to do with perception. People are still perceiving that remanufactured products are not as good as the original product. And then some people might say also that it's not so prestigious to use a remanufactured product. They prefer to buy brand new. So education is important. We need to tell people, more and more people, that remanufactured product, if they are remanufactured according to the British standard or the American standard, then they should be at least as good as the original product. And if you explain to them how that can be achieved, then more and more people will understand. And then when they realize also the benefits, the environmental benefits of remanufacturing, I think more people will be converted.
That's great. What do you think is going to be the impact of this work, of your work, or of the work of colleagues on remanufacturing, on employment in the long term?
You know, as with any automation, there will be a reduction in labor. But as you can see, the labor content of remanufactured product is very high, and the potential of remanufacturing is not yet exploited fully. So if more and more products are remanufactured, there'll be more and more people required. So despite the fact that the percentage per product is reduced, the number of products remanufactured will be increased. So I would say that at least in the field of remanufacturing, automation will not reduce the overall labor content.
That's great. I'm going to change a little bit the way of or the content of what we're talking about right now. Remanufacturing is part of circular economy, and circular economy has a number of different options when it comes to closing the circle. So can you help the audience understand a little bit the difference between refurbishing and remanufacturing?
Yeah. So refurbishing often is to do with making something look good. It also can function. You know, you make a something that doesn't work. You can make it work, and you can make it look also almost as new, but it doesn't follow this standard. You know, the standard that requires that the remanufactured product has to be at least as good as the original product. So if you do refurbishing and you achieve that standard, then you have remanufactured. So the difference is this standard.
Great, thank you. There is a very interesting question on the Q&A chat that has to do with the design for remanufacturing. How do you think your research contributes to the design for remanufacturing, and whether through your work we can come up with ways of designing for remanufacturing that can be more effective, more efficient?
This is a very important topic, obviously, yes. When you do disassembly, when you study the mechanics of disassembly, you find what causes parts to become trapped, to become wedged, and because of that, you can modify the parts and enable the new generation of parts to become easier to disassemble. For instance, you find that in this, if you want to promote disassembly, you must not use, let's say, glue. You must use as many pilots and chamfers as you can on the male components in order to avoid wedging of the components. So there are different things that you can do. And you can only do that by understanding what causes disassembly to be difficult.
That's really important. You've been tracking this area for quite a lot of time. You know the state of the art. Have you seen, or is there any evidence that basically more products are designed nowadays having this into mind? So more OEMs deciding to produce, to develop products that can be remanufactured in the future?
The number is increasing, but I'm not saying that it is happening enough yet.
Okay. So another interesting question from the Q&A tab. What makes differences from disassembly sequence to the assembly sequence in the planning process? So how would robotic techniques help in the disassembly sequence planning problems?
How does...
So the fact that we are using robots, I'm trying to interpret the question as well. The fact that we are using robots, what would be the impact on the assembly sequence in the planning process?
Yeah. So when we do robotic disassembly, we need to think about the tools that the robots use. We need to think about tool changing, the time required for tool changing. With people, it's very, very quick to change tools. With robots, it could take time. So planning has to take into account uh, the changing of tools, has to take into account the access of the tools. With people, having access is not a problem. With robots, as you can see, we had that screwdriver that was too weak to get into a slot, and you have to plan properly, otherwise you cannot perform the disassembly. So there are some differences, some I would say tactical differences between human disassembly and robotic disassembly, and you need to take into account those differences.
Oh, that's great. More and more questions are coming up, which is really interesting, and shows the fact that the audience has a lot of interest on the topic. Since we're talking about humans and robots and the fact that they will have to collaborate together, how is human safety taken into consideration? How do we ensure that human safety is secured in a sense when it comes to that sort of collaboration between humans and robots?
Yes, I should have mentioned that in our case, we use a type of robot known as collaborative robots. So they are inherently safe. They will not damage people. We need to be careful that the tools they use are also safe for people. So using collaborative robots is one thing that we would recommend when you want to use people and robots together in close proximity. If you need to have robots and people separated from each other, that is possible, but then it requires fencing. It slows things down. So using human robots together, it's best to use collaborative machines.
That's great. There is a question about the reliability of the remanufactured products. Would you like to comment on that?
So this is similar to the perception that I mentioned before. People think that remanufactured products are not as reliable as original product, but then those, I would not call them remanufactured products. They are probably refurbished or reconditioned products, because if they are remanufactured according to British standard, then they should be at least as reliable as the original product, because you use the same components, you use the same quality assurance procedures, and sometimes you use even better components.
That's great. Before closing this very interesting session, I've got a question of my own to ask, Jack. How do we know when is the right time in the life cycle for a product to be remanufactured? How can we make these sort of informed decisions so that we can decide when is the right time to maximize the retained value of the product?
Yeah. So it involves experimentation. Yeah, you need to experiment. Let's say if you are using a bearing, you need to experiment and you need to see that when a certain level of vibrations is achieved, then the bearing needs to be replaced. Yeah. So you monitor the vibrations, and then when that level of vibrations is achieved, then you say, okay, the product is ready for remanufacture. And in our case, we have a study done by our colleague, and she predicts when the bearing will become will become faulty. So not only do we detect when it is faulty, we can predict when it might become faulty. After 24 hours, we need to replace it.
That's great. Thank you very much, Doug, for this presentation and the discussion that follows the presentation. There are more questions. Unfortunately, we don't really have the time to run through all the questions, but you've given your contact details and the details of the laboratory at Birmingham University, and I'm pretty sure that people will probably contact you to ask further questions if they have more interest on the topic. Again, thank you very much for this excellent talk today.
Thank you very much, Kostas. Thank you, everybody. Bye-bye for now.
Bye-bye for now.
Bye.